In this video, I will be discussing about second-order differential equation reducible to the first order. Actually, there are three special cases of the second-order differential equations reducible to the first order. And the method to be used in solving this kind of equation will employ the substitution that uses a third variable to accomplish the reduction of the second order to the first order. Note that in the complete solution, there must be two arbitrary constants here, since the differential equation under consideration is of the second order. So let's take the first case. A second-order differential equation having the form d by dx of the dy dx plus y times a function of x which is equal to b of x can be reduced to a first-order differential equation when you let your u be equal to this expression inside here. So when this will be your u, you can rewrite this one as d by dx of your u, which is equal to b of x. Because instead of writing this one, you will write its representation, which is u. And rewriting this one, we have du, which is equal to b of x dx. Then we can integrate both sides of the equation because the variables are now separated. So this is the integral of du and the integral of b of x dx. So therefore, our u this time is equal to the integral of b of x dx plus the constant of integration c sub 1. And because this is our u, we can substitute this one to our representation. So we say that this is our u, which is the integral of b of x dx plus the constant of integration c sub 1 is equal to the derivative of y with respect to x plus y times a of x. So here, after integrating this one, we still have one derivative here, which is dy dx, and the resulting equation is now a first order differential equation, which is linear in y. So this is now a first order linear differential equation. And we know how to solve this one already using the method which we've learned in solving a first order differential equation, because this is linear in y. Now, another case is when you have a second order differential equation and when you have a missing y here. So in the equation, you have the second derivative term, you will have the first derivative term, you have your x variable, but you don't have the y variable. So when this happens, this differential equation can be reduced to a differential equation of the first order when you let your first derivative as your p here. And if you get the derivative of p with respect to x, that is already the second derivative of your y with respect to x. So here, our first derivative is represented as a variable, and our second derivative is represented as a first derivative. So the resulting differential equation is now in the form of a first derivative, because the first derivative is represented like a variable, and the second derivative, which is the derivative of the variable, is represented like a first derivative. So substituting these representations here to our differential equation, we have our differential equation, instead of writing the second derivative, I will write dp dx, which is the first derivative of p. And the first derivative is now our p here. So our newly transformed differential equation is now on the first derivative form, because the second derivative is transformed to a first derivative, and the first derivative is transformed to a variable. But you can see here that there is no y variable, and we know that this is now a first ordered differential equation. And assuming that this final solution will take the form of p, which is equal to some function of x plus the constant of integration c sub 1, then the substitution p, which is equal to the derivative of y with respect to x, will give the final solution of y, which is equal to the integral of f of x plus the constant of integration c sub 1 dx plus the constant of integration c sub 2, because you are integrating here twice already. Because when you solve this first order differential equation, you are integrating and the result contains the first arbitrary constant. But remember that our p is originally a first derivative. So you need also to integrate again for the second time and obtain the second arbitrary constant. Now let's proceed to case number 3. A second ordered differential equation with x missing. So this is different from case number 2, because in case number 2 the y is missing, but here in case number 3 the x is missing. So when you have a differential equation when there is no x variable, then that second order differential equation can be transformed to its equivalent first order differential equation by substituting your first derivative as p and your second derivative as dp dx. But there is a little problem here, because we know that p is not in terms of x, because in the equation there is no x. So how can you get the derivative of p with respect to x? So in this case, we will now apply the notion of the chain rule, that to get the derivative of p, we need to find the derivative of p with respect to y, because our equation has no x but y. So we get the derivative of p with respect to y and then get the derivative of y with respect to x. So this is our second derivative of y with respect to x. And we know that dy dx is our p. So this is dp dy times p is our second derivative of y with respect to x. Or you can rewrite this as p times derivative of p with respect to y. And again, this is the second derivative of y with respect to x. So instead of writing the second derivative of y with respect to x, you will write p times the derivative of p with respect to y. So what happens is that in our differential equation, instead of writing the second derivative, we will write p times the derivative of p with respect to y, because there is no x here. And then instead of writing the first derivative, I will write p. And of course, we have the variable y here. And you notice that this is now a first ordered differential equation. So you solve this first ordered differential equation the way we solved in the previous video, and then after solving, we substitute the value of p, which is dy dx. So the resulting equation is not the final solution, but still a first order differential equation. So you integrate for the second time, and then you obtain the second arbitrary constant. So in the final solution for this case number 3, we expect that there are two arbitrary constants, the c sub 1 and the c sub 2. So the final solution is an equation that contains x and y, and the first arbitrary constant c sub 1 and the second arbitrary constant c sub 2, which is equal to 0. Now let's take our first example here. Find the complete solution for this differential equation. So we notice that this differential equation takes the form of case number 1 because we have a derivative of a first derivative, and this is equated to some functions of x, like here. So we say that this differential equation takes the form of case number 1. So we represent what is inside here as your u. So u is equal to the derivative of y with respect to x plus y. And substituting this one to the given differential equation, we have the derivative of our u, which is this one here, is equal to e to the power negative x. And rewriting this equation, we have du, which is equal to e to the power negative x dx. And you see that the variables are separated already. So we can integrate both sides of the equation here. So this is the integral of negative x dx. And we know that the integral of du is u. But the derivative of e to the negative x is not dx, but negative dx here. And to neutralize this added negative here, we need to multiply negative 1 in front of the integral symbol. So we have u, which is equal to the negative of e to the power negative x plus the constant of integration c sub 1. So this is now our u, and substituting this u in our representation, we have negative e to the negative x plus c sub 1 is equal to the derivative of y with respect to x plus y. Because instead of writing u, I will write its equivalent value. And you notice that this is already a first order linear differential equation because this is linear in y. And rewriting this one so that we can easily see that this is a first order linear differential equation, we can rewrite this one at the left side of the equation, and this left side will be at the right hand side here, so that we can easily see that this is our a of x and this is our b of x of our first order linear differential equation. So with this one, we can find our integrating factor phi of x. So this is e raised to the exponent of the integral of a of x dx. And we know that our a of x is 1 there. So our phi of x is e raised to the exponent of the integral of dx. And the integral of dx is x. Therefore, our integrating factor is e to the power x. So multiplying this equation by the integrating factor e to the x, we have e to the x times the negative of e to the negative x plus e to the x times c sub 1, which is this one here. And this is equal to e to the x times the derivative of y with respect to x plus e to the x times y, which is this one. So we are multiplying each term in this equation by the integrating factor e to the x. So we have negative 1 because e to the x times e to the negative x is e to the power 0, and e to the power 0 is 1. So we have this negative 1 plus c sub 1 e to the x, which is equal to e to the x times the derivative of y with respect to x plus e to the x times y. And you must be clever enough to see an integrable combination here, because this sum is already a derivative of a product of e to the x and y. So this is the derivative of a product with respect to x. And you can check that this is e to the x times the derivative of y with respect to x plus y here times the derivative of e to the x, which is e to the x. And this is equal to c sub 1 e to the x minus 1 at the left. So rewriting this equation, we have c sub 1 e to the x minus 1 dx is equal to the differential of e to the x times y. And integrating both sides of the equation, we have this c sub 1 times the integral of e to the x dx minus the integral of 1 dx, which is equal to the integral of the differential of e to the x times y. And we know that the integral of the differential cancels each other. So this is e to the x times y. And this is c sub 1 times e to the x minus x plus the constant of integration c sub 2. And so that you will not be confused of these two arbitrary constants, we can rewrite this c sub 1 as a. So a times e to the x minus x plus b, which is equal to e to the x times y here. And this is our solution for this second ordered differential equation, that we solve this one by reducing the order to the first order and then substituting back our representations, then solve again for the resulting equation. Now let's proceed to our example number 2. Determine the general solution for this differential equation. And as you can see that this differential equation takes the form of case number 1. So to solve this differential equation, we represent u as the expression inside the parentheses. So u is equal to x times dy dx plus 2y. So substituting this representation to the given differential equation, we have the derivative of our u, because instead of writing this one, I will write u, which is my representation of what is inside the parentheses, and this is equal to negative 2 times x to the power negative 3. And rewriting this equation, we have du, which is equal to negative 2 x to the power negative 3 dx. So now that the variables are separated, we can integrate both sides of the equation here. So this is the integral of negative 2x to the power negative 3 dx. And we know that the integral of the differential cancels each other. But we can factor out the negative 2 outside the integral symbol. We have negative 2 times the integral of x to the power negative 3 dx. And using the power rule in integration, we have negative 2 times x to the power negative 2 over the negative 2 plus the constant of integration c sub 1. So our u is equal to x to the power negative 2 plus c sub 1. Then substituting this value of u in our representation, we have x to the power negative 2 plus c sub 1 is equal to x times the derivative of y with respect to x plus 2y. And to eliminate this factor of x here, we need to divide both sides of the equation by x. So we have x to the power negative 2 plus c sub 1 over x, which is equal to the derivative of y with respect to x plus 2y over x. And rewriting this equation so that the right hand side of this equation will be at the left hand side, we have the derivative of y with respect to x plus 2 over x times y, which is equal to x to the power negative 2 over x plus c sub 1 over x. And you can observe that this is already a first order linear differential equation, because you can see that this is linear in y. So rewriting further this differential equation, we have the dy dx plus the 2 over x times y, which is equal to x to the power negative 3 plus c sub 1 x to the power negative 1. Because the exponent of x here, when moved to the numerator, will have an exponent of negative 1. So negative 2 plus the negative 1, we have negative 3. And this one is also negative 1 exponent in the numerator. So we understand that this is our a of x, and this is our b of x here. Thus, our integrating factor, which is the phi of x, is equal to e raised to the exponent of the integral of a of x dx. And we know that our a of x is 2 over x here. So factoring the 2 outside the integral symbol, we have the 2 times the integral of dx over x. And we know that the integral of dx over x is ln x. And using the property of logarithms, these two can be the exponent of x. And we know further that this e and the natural log cancels each other. So therefore, our integrating factor is x squared. Hence, when we multiply all the terms in the equation by x squared, we have x squared times the derivative of y with respect to x plus x squared times 2 over x times y, and this is equal to x squared times x to the power negative 3 plus x squared times c sub 1 times x to the power negative 1. So simplifying further, we have x squared derivative of y with respect to x plus 2x times y, which is equal to x to the power negative 1 plus c sub 1 x. And you must be clever enough to notice that this is already an integrable combination because this is a derivative of a product of x squared and y. So this is the derivative with respect to x. So here we have x to the power negative 1 plus c sub 1 x. Now rewriting our equation, we have the differential of x squared times y, which is equal to x to the power negative 1 plus c sub 1 x dx here. Then we can integrate both sides of the equation here, and the integral of the differential cancels each other. So we have this integral of dx over x plus c sub 1 times the integral of x dx. So integrating further, we have this natural log of x plus c sub 1 over 2 times x squared plus the constant of integration c sub 2. So that we will not be confused by this coefficient here, because c sub 1 is constant, when divided by 2 that is a constant, the quotient is still a constant. So I will rewrite our answer as x squared times y, which is equal to the natural log of x plus a times x squared plus b here, where a and b are our arbitrary constants in the solution of this differential equation. So this is now our final solution. Now let's proceed to our example number 3. Find the complete solution for this differential equation. Now, looking at this differential equation, we observe that the y term is missing in the equation. So the equation takes the form of case number 2. So we use the representation of p for our first derivative of y with respect to x. And if you take the derivative of your p, which is the first derivative of y with respect to x, then this is already the second derivative of y with respect to x. So substituting our representations of p and dp dx in our differential equation, we have x squared times the y double prime, which is the second derivative of y with respect to x. So this is multiplied by dp over dx plus 3x times y prime, which is the first derivative of y with respect to x. So instead of writing y prime, I will write p there because that is our representation. Now to eliminate this x squared as a factor of the derivative of p with respect to x, we need to multiply both sides of the equation by 1 over x squared. So we have the derivative of p with respect to x plus 3x over x squared p, which is equal to 2 over x squared. So rewriting our equation, we have derivative of p with respect to x plus 3 over x times p, which is equal to 2 over x squared. And you notice that this is already a first order linear differential equation because this is linear in p. So our a of x here is this 3 over x, and our b of x is equal to 2 over x squared. Thus, we can find our integrating factor phi of x that this is equal to the e raised to the exponent of the integral of a of x dx. But we know what is our a of x because our a of x is 3 over x dx. So this is e raised to the exponent of 3 when you factor out 3 outside the integral symbol. So our phi of x is equal to e raised to the exponent of 3 times the natural log of x. And using the properties of logarithm, this 3 can be the exponent of x. So e raised to the exponent of the natural log of x cubed. So therefore, our integrating factor is x cubed because this e and this ln cancels each other. Hence, if you multiply this integrating factor to each term in this equation here, we have x cubed times the derivative of p with respect to x plus x cubed times 3 over x times p, which is equal to x cubed times 2 over x squared. And rewriting our equation, we have x cubed times the derivative of p with respect to x plus 3x squared p, which is equal to 2x here, because x cubed divided by x squared is x. And you notice that this sum is a derivative of a product. So this is a derivative of a product x cubed and p here. And you can check that you have your x cubed there times the derivative of your p plus your p times the derivative of x cubed, which is 3x squared. So rewriting this equation, we have the differential of x cubed times p is equal to 2x dx here. So we can now integrate both sides of the equation, and we know that the integral of the differential cancels each other. So what remains is x cubed times p, which is equal to the integral of 2x, which is 2 times x squared over 2, plus the constant of integration c sub 1. So simplifying our answer, this is x cubed times p, which is equal to x squared plus c sub 1. But we know that our p is the derivative of y with respect to x. So substituting our original variable, we have x cubed times dy dx, which is equal to x squared plus c sub 1. So to eliminate this x cubed here, we need to multiply both sides of the equation by 1 over x cubed. So we have the derivative of y with respect to x, which is equal to x squared over x cubed plus c sub 1 over x cubed. And rewriting this equation further, we have the derivative of y, which is equal to x to the power negative 1 plus c sub 1 x to the power negative 3 dx. We can now integrate both sides of the equation. So we have the integral of dy and the integral of this one here. And we know that the integral of the differential cancels each other. So this is equal to the integral of dx over x for this term here. And this is added to c sub 1 when you factor out of the integral of x to the power negative 3 dx. So we have y, which is equal to the natural log of x plus c sub 1 times x to the power negative 2 over the negative 2 plus the constant of integration c sub 2. And so that we will not be confused by this c sub 1 over the negative 2, we will replace that one by a and b. So y is equal to the natural log of x plus a times x to the power negative 2 plus b here. And this is our solution for this differential equation, where a and b are the two arbitrary constants in this final solution. Now let's proceed to our example number 4. Find the complete solution for this differential equation. Now, looking at this differential equation, we notice that this differential equation takes the form of case number 2, because we have a missing y variable here. We have the x variable but we don't have the y variable, different from the y double prime and the y prime. Now, since this is a second case, we represent our first derivative of y with respect to x, as our p. And if you take the derivative of p with respect to x, this is already the second derivative of y with respect to x. So, since our original differential equation is y double prime, which is equal to x plus y prime quantity raised to the second power, instead of writing y double prime, we will write the derivative of p with respect to x, because this is the second derivative of y with respect to x. And instead of writing y prime, I will write p, because that is our representation here. Now, looking at this transformed differential equation, we can solve this differential equation by the method of substitution that is suggested by this differential equation. And we discussed that method in the previous video. So if you have not watched that video, I will advise you to watch that video first. So let us represent this x plus p by a new variable z here. So solving for p, we have z minus x is our p. So taking the derivative of z with respect to x, we have dz dx minus 1 is equal to the derivative of p with respect to x, because the derivative of x with respect to x is 1. So this is our value of dp dx. So substituting this representation, we have dz dx minus 1, which is equal to z squared. Because instead of writing dp dx, I will write this one here. And instead of writing x plus p, I will write its representation, which is z. So our dz dx is equal to z squared plus 1. And you notice that this is already a separable differential equation, because we can move this z squared plus 1 as the denominator of dz. And we can do that by multiplying dz dx and also z squared plus 1 by the reciprocal of z squared plus 1. And also to eliminate this dx, I need to multiply dx here. So dx and the dx cancels each other. So we have dz over z squared plus 1, which is equal to dx here. So now we can integrate both sides of the equation, that the integral of dz over z squared plus 1 is the arctangent of z here. And you can check that That is the integral of this fraction by recalling your knowledge from your previous calculus. So taking tangent to both sides of the equation, we have z is equal to tangent of x plus c sub 1. And we know that our z is x plus p. So x plus p is equal to the tangent of x plus c sub 1. So subtracting both sides of the equation by x, we have p equals the tangent of x plus c sub 1 minus x. But we know that our p is the derivative of y with respect to x. So we can substitute it here for our p. So dy dx is equal to the tangent of x plus c sub 1 minus x. And rewriting this equation, we have differential of y is equal to the tangent of x plus c sub 1 minus x quantity dx. And now we can integrate both sides of the equation. So y is equal to the integral of the tangent of x plus c sub 1 minus the integral of x dx. And we know from your integral calculus that the integral of tangent is the natural log of the secant of x plus c sub 1 here. And this is subtracted by x squared over 2 plus the constant of integration c sub 2. Now, eliminating this denominator of 2 here, we need to multiply both sides of the equation by 2. So we have 2y, which is equal to 2 times the natural log of the secant of x plus c sub 1 minus x squared plus the constant of integration c, because 2, which is a constant, times c sub 2, which is a constant, the product is still a constant. And so that you will not be confused by these two arbitrary constants here, we will rewrite our final solution as 2y, which is equal to twice of the natural log of the secant of x plus a minus x squared plus b, where a and b are the two arbitrary constants here. And this is our final solution for this differential equation. Now let's proceed to this example number 5. We noticed that this differential equation takes the form of case number 3, because here we have the variable y but we don't have the variable x. So this is the second order differential equation without the variable x. So what is missing here is the variable x. So if this is the case, we will use our representation of p, which is dy dx, and our derivative of p with respect to x, which is actually the second derivative of y with respect to x. But there's a problem because we cannot find the derivative of p with respect to x because we don't have the x here. So what we will do is to apply the concept of chain rule, that we need to find the derivative of p with respect to y times the derivative of y with respect to x, because this is the second derivative of y with respect to x, and we know that this one is our p. So instead of writing this one, I will write p. So p times the derivative of p with respect to y is our second derivative of y with respect to x. So, since our differential equation is y times y double prime plus the square of prime, which is equal to 2y prime, can be rewritten as y times the double prime, which is this one here, p times the derivative of p with respect to y, because this is the second derivative of y with respect to x, or in other words, that's the y double prime, plus p quantity squared, because the y prime is our first derivative of y with respect to x, and this is equal to 2p, because this is a first derivative of y with respect to x. So eliminating this p here, we need to multiply both sides of the equation by 1 over p. So we have y times the derivative of p with respect to y plus p, which is equal to 2. And to eliminate this y here, we need to multiply again both sides of the equation by 1 over y. So we have the derivative of p with respect to y plus 1 over y times p, which is equal to 1 over y times 2. And we notice that this is already a first order linear differential equation, which is linear in p. So this is our a of y, and this is also our b of y here. Thus, our integrating factor, which is phi of y, which is equal to e to the power of the integral of a of y dy, and we know what is a of y. A of y is 1 over y here. So we have e to the power of the integral of dy over y. And we know that the integral of dy over y is ln y, and e and the ln cancels each other. So we have our integrating factor, which is y. Then we can use this integrating factor to multiply to each term in our equation. So y times dp dy plus y times 1 over y times p, which is equal to y times 2 over y. So this is y times the derivative of p with respect to y plus p, which is equal to 2. And you must be clever enough to notice that this is already an integrable combination, because this is a derivative of a product of y and p. So this is the derivative with respect to y, and this is equal to 2. And you can check that we have a y here times the derivative of p with respect to y plus p times the derivative of y with respect to y, which is 1. And then rewriting this equation here, we have the differential of y times p, which is equal to 2 dy. So integrating both sides of the equation, we have y times p, which is equal to 2y plus the constant of integration c sub 1. But we know that our p is the derivative of y with respect to x, because we just treat this first derivative as simply a variable. So substituting this one here, we have y times the derivative of y with respect to x which is equal to 2y plus c sub 1. And we notice that this is already a separable differential equation. And to do that, we will eliminate this dx here by multiplying both sides of the equation by dx. So we have y dy, which is equal to 2y plus c sub 1 dx. And so that we can eliminate this factor of dx, because this is in terms of y, we will multiply both sides of the equation by 1 over 2y plus c sub 1. So we have y over 2y plus c sub 1 dy, which is equal to dx here. Now we notice that this fraction is an improper fraction because the degree of the numerator, which is 1, is the same with the degree of the denominator, which is also 1. So of course we need to divide the numerator by the denominator here, which is 2y plus c sub 1. So when y divided by 2y, we have 1/2, and 1/2 times 2y is y, and 1/2 times c sub 1 is c sub 1 over 2. So subtracting these terms here, this is 0, and this is 0 minus c sub 1 over 2 is negative c sub 1 over 2. So we can rewrite this fraction here as 1/2 minus c sub 1 over 2 all over this divisor 2y plus c sub 1, and this is equal to dx. So integrating each term in this equation, we have 1/2 times the integral of dy minus c sub 1 over 2 times the integral of dy over 2y plus c sub 1, and this is equal to the integral of dx. And if you let this denominator as your u, the du is not only dy, but it is 2 dy. So we have 1/2 of the integral of dy minus c sub 1 over 2 times the integral of 2 dy over 2y plus c sub 1. And to neutralize this added factor here of 2, we need to multiply outside the integral symbol by 1/2, so that 1/2 times 2 is just 1. So as if I have done nothing to this term here. And this is equal to the integral of dx. But we know that the integral of dy is y, and this is c sub 1 over 4 times the integral of this fraction, which is the natural log of 2y plus c sub 1, which is equal to x plus the constant of integration c sub 2. So to make this 1/2 as a whole number, I need to multiply both sides of the equation by 2. So we have y minus c sub 1 over 2, because 2 over 4 is 1/2, times the natural log of 2y plus c sub 1, which is equal to 2x plus c sub 2, because 2, which is a constant, times another constant, the result is still a constant. And we say that this is our final solution to this differential equation. Now let's proceed to our example number 6, our last example. Now you notice that this differential equation, we don't have the variable x. So we say that this differential equation takes the form of case number 3. So we let p as our derivative of y with respect to x, and taking also the derivative of p with respect to x is our second derivative of y with respect to x, because here we treat the first derivative as a variable, and when we differentiate this variable, that is already the second derivative of y with respect to x. But again, we have a problem because we cannot take the derivative of p with respect to x, because in the equation we don't have an x. So we use the concept of the chain rule that we get the derivative of p with respect to y, and then take also the derivative of y with respect to x, and the result is actually the second derivative of y with respect to x. And we know that this one is our p. So instead of writing this dy dx, we will write p here. So p times the derivative of p with respect to y is actually the second derivative of y with respect to x. So since our given differential equation is 2y y double prime plus y squared, which is equal to the square of y prime, then we can substitute our y double prime by this one here. So we will write p times the derivative of p with respect to y, and this is added to y squared, which is the square of p here, because p is the first derivative of y with respect to x. Now eliminating this denominator of dy here, we need to multiply both sides of the equation by dy. So we have 2yp times dp plus y squared dy, which is equal to p squared dy here. Now moving this term to the left side of the equation so that these two dy's can combine, we have 2yp times dp plus y squared minus p squared times dy, and this is equal to 0. And you notice that this is not a separable differential equation because of this y squared minus p squared here, but this is a homogeneous differential equation. And how do I know that this is a homogeneous differential equation? Because the sum of the exponent here, which is y and p, is 2. The exponent of y is 1, the exponent of p is 1, so 1 plus 1 is 2. And the exponent here is 2, the exponent here is 2, so therefore this is a homogeneous differential equation. And as you can see, that this equation is in terms of two variables, which are p and y, but we use p here because the multiplier of dp is simpler than the multiplier of dy. So we will use our substitution of p, which is equal to vy. So taking the derivative of p, which is equal to the derivative of the product, which is v dy plus y dv here. So substituting this one to our differential equation, we have 2y times p, which is vy, times dp, which is v dy plus y dv plus y squared minus p squared, and our p is vy. So when we square, that's v squared y squared times dy, which is equal to 0. And rewriting this equation, we have 2v y squared times v dy plus y dv plus y squared, because when you factor out y squared here, we have 1 minus v squared times dy, which is equal to 0. Now that we have a common factor, which is y squared for these two terms, we eliminate by multiplying both sides of the equation by 1 over y squared. So we have 2v squared dy. If you distribute this one here and also distribute this to this second term, we have plus 2vy dv plus dy minus v squared dy. If you distribute this dy to this binomial here, and this is equated to 0. So combining similar terms, this one and this one here, we have 2 minus 1, so we have 1v squared dy plus dy, this term, plus this 2vy dv, which is equal to 0. And factoring the common factor, which is dy, we have v squared plus 1 times dy plus 2vy dv here, which is equal to 0. And we noticed that this is already a separable differential equation. So to move this v squared plus 1 as the denominator of this second term, we need to multiply both sides of the equation by 1 over v squared plus 1. So multiplying each term of the equation by this 1 over v squared plus 1, we want also to eliminate this y here. So multiplying this v squared plus 1 by y here. So this v squared plus 1 with this one cancels. What remains is dy over y plus this 2v dv over v squared plus 1, and this is equal to 0 because this y here and this y cancels each other. So what remains is 2v dv over this v squared plus 1. Now integrating each term in this equation, this is the integral of dy over y plus the integral of 2v dv over v squared plus 1, which is equal to the integral of 0. So we have the natural log of y plus the natural log of v squared plus 1, which is equal to the constant of integration c sub 1. Because if you take this v squared plus 1 as your u, your du is here 2v dv. But since p is equal to vy, then we can get our v by dividing both sides by y. So v is equal to p over y. So substituting this value of v to our transform equation, we have ln y plus the natural log of v squared, which is p squared over y squared, plus 1 is equal to the constant of integration c sub 1. Now moving this ln y to the right, we have the natural log of p squared over y squared plus 1 is equal to the natural log of c sub 1 minus ln y. And you might ask a question, why is it that c sub 1 became ln of c sub 1? Because c sub 1 is a constant, then therefore the natural log of a constant is still a constant. And I do that so that I can combine the two. So we have ln of p squared over y squared plus 1 is equal to the natural log of c sub 1 over y. Now, raising both sides of the equation to e, we have p squared over y squared plus 1 is equal to c sub 1 over y. And moving this 1 to the right, we have p squared over y squared, which is equal to c sub 1 over y minus 1. And combining the two terms at the right, we have this y as the LCD of the two. So this is c sub 1 minus y. Now, eliminating this y squared here, we need to multiply both sides of the equation by y squared. So we have p squared, which is equal to y times c sub 1 minus y. So therefore, p is equal to the square root of the product of these two, which is c sub 1y minus y squared. But we know that our p is the derivative of y with respect to x. So we substitute this 1 to this equation. So we have dy dx, which is equal to the square root of c sub 1y minus y squared. And rewriting this equation, we have dy over the square root of c sub 1y minus y squared, which is equal to dx. Now, to integrate this fraction here, we need to complete the square inside the radical symbol. And to do that, we have to factor first the negative here. So this is negative y squared minus c sub 1y. And this is equal to dx. So to complete this radicand to form a perfect square trinomial, we have to get the half of the second coefficient here, which is c sub 1, and then we square the half, and the half is c sub 1 over 2. So this is the added term here, but actually we are not adding because we have a negative outside the parenthesis. So we are subtracting this term from this one. So to balance, we have to add same term here. And this is equal to dx. So derivative of y over the square root of the square of c sub 1 over 2 minus the square of y minus c sub 1 over 2. So if you let your a be this constant c sub 1 over 2 and your u be y minus c sub 1 over 2, then your du is equal to dy, because the derivative of this is 0, because this is a constant here. So substituting these representations to this fraction here, we have du over the square root of a squared minus u squared, and therefore we can now easily integrate these terms here, because we know the integral of this one, that this is equal to the arc sine of u over a, which is equal to x, the integral of dx, plus the constant of integration c sub 2. And our u is y minus c sub 1 over 2 divided by a, which is c sub 1 over 2, which is equal to x plus c sub 2. Now, simplifying our numerator there to form one fraction, we have 2y minus c sub 1 over 2 divided by this one. So we multiply by the reciprocal of this 2 over c sub 1, which is equal to x plus c sub 2. And this is cancelled here. So arc sine of 2y minus c sub 1 over c sub 1, which is equal to x plus c sub 2. And simplifying this term here, we have the arc sine of 2 over c sub 1y minus 1, this term, which is equal to x plus the constant of integration c sub 2. So that you will not be confused by this constant, I will rewrite that constant as a here. So ay minus 1, which is equal to x plus b, where a and b are then arbitrary constants in this final solution for this differential equation. And that's it. If you learned something today, please check out my channel for more videos like this and click subscribe. Click the notification bell below so you'll get notified whenever I'll be posting a new video. Don't forget to like this video to show your support. And always remember to math your way up. Thank you.